Alright, welcome back. In the last video I introduced this formula for integration by parts, which reverses the product rule. But I didn't yet show an example of how to use it. And it may look mysterious at this point. What is this U, what is this V, and DU, DV? It looks really confusing. But it's a type of bookkeeping notation. It's for keeping track of all the terms in the expression and making sure you don't lose anything. I'll show you how to use this method for an integral that we already know the answer for, the integral of x times the cosine of x. And the reason we already know the answer is because we took the derivative of the expression that was given to us to verify that it's the answer. But we're going to pretend that we don't have that. We're going to pretend we don't have what the antiderivative is, and we're just going to find it from scratch. So I'm going to identify that this is an IBP question, integration by parts. Which means that I have to express this integral as u times dv. So some part of this I have to call u, and some part of this I have to call dv. X times the cosine of x dx is equal to u times dv. Some part of x cos of x dx is u, and the rest is dv. Note, it should be obvious that the dx part is always going to be inside the dv part. dv always gets the dx, and it will sometimes get one term and sometimes get the other term. So the x will sometimes be part of the u and sometimes it'll be part of the dv, depending on the question that you're working on. And I'll show you later on one heuristic that could be used to select how to split your integral into those two pieces. So I'm going to try u equals x. Now dv has to be everything else. And dv is equal to cosine of x dx. Because when I multiply those two things together, I get back my x cos of x dx. I get back my u dv. So my formula says that this is going to be equal to uv minus the integral of v times du. Now notice that already we have identified what u is equal to. It's equal to x, but we don't have anything else. So I have an x, and I leave a space for the v. I have a space for this v. I have to leave a space for the du. So let's find out those pieces. I'm going to take the derivative of u. Du by dx is equal to 1, and then rearrange. So du is equal to dx. Well, that part was easy. U is just dx. Now I need v, and v is going to appear in two different spots. How do I get v? I'm going to get v from dv. To get v from dv, I'm going to integrate both sides of the expression. Okay, the antiderivative of 1 with respect to v is just v. This is similar to taking the antiderivative of 1 times dx, which is just x. So on the left-hand side I get v, and this will always happen. We'll always get v on the left-hand side when we integrate dv. Right-hand side, the antiderivative of cos of x with respect to x is sine of x. We do get a plus c as well. And I'm going to tell you now to ignore it at this stage of the calculation. We'll take care of it later. All right, so everything's been taken into account. We put in the u, the v and the du. We put them all into the expression. It's got some extra brackets and may look a little bit messy, but I'm just going to clean it up. I'm going to rewrite it. X sine of x minus the integral of sine of x dx. Okay, and now we can take the antiderivative. Before I just pause, look at this, what we started with, x times cosine of x. We don't know how to take the antiderivative of that, so we've replaced it with a function, which is, you don't need to integrate x sine of x, that thing that's in front, minus a new integral. And the new integral is much nicer. The antiderivative of sine of x is simple. It's something that you have on your list of antiderivatives, something that you may have memorized. Antiderivative of sine of x is negative cosine of x. And now we can tack on that plus c. And then we can simplify x sine of x plus the cosine of x plus c. And if we flip back to earlier in the note, when that was essentially the question, what is the antiderivative of x times, or wait, where was it? X times cos of x, how do you find the antiderivative of x times cos of x? We didn't answer this yet until just now. We now know that the answer, the antiderivative of x times cosine of x, is this, x sine of x plus cosine of x plus c. And we would verify that using the derivative. So at no stage do we have something like a substitution. I don't have to go back and change the u and the v to anything. At the end, our answer is natural in terms of x. It's a very different type of transformation. We're not transforming the axis like we are when we do a substitution. What we're doing is we're just breaking up the integral into a function minus a new integral. And we're hoping that the new integral is easier than the first integral. So it's a different philosophy for rewriting the problem. So one natural question that everyone should be thinking about is that first step that we had to do was splitting up x cos of x dx into u times dv and making a choice that u is equal to x and dv is equal to everything else. There is another natural choice we could try. What if we let u equal cosine of x? So I'm going to try it and show you what happens. We have integral of x cos of x dx is equal to integral of u dv. And integration by parts says that's equal to uv minus the integral of v du. Now, if we use the split that was just proposed, u equals cosine of x, then dv must be everything else. So we haven't yet taken the x or the dx, so that's going to be my dv. Now I'm going to take the derivative of u. Du by dx is negative sine of x. So du is equal to negative sine of x times dx. So that's going to go here for du. And then for dv, I'm going to integrate both sides of dv, of the dv expression. Integral of dv is equal to integral of x dx. So v is equal to 1/2 x squared. So that'll go in the v part of the expression. So we have u, which is cosine of x, minus integral of v times du. So 1/2 x squared, 1/2 x squared for v, and then du negative sine of x dx. And then rewrite 1/2 x squared times the cosine of x, just putting the constant out front, polynomial after, and the trig at the end. For the second piece, we have a negative and a negative multiplying, so that's going to make a positive. I'll bring the 1/2 out front of the integral. Integral of x squared sine of x dx. And this is worse. We've gone from the integral of x cos of x dx to the integral of x squared times the sine of x. So the power on x is increased by 1. We're getting further than we started with. This integral is worse than integral of x cos of x dx. Power on x increased. Integrations you've seen already with substitution. You've seen already just prior to substitution, just doing antiderivatives by memory, memorizing what the derivative of something is and using that to find the antiderivative of something. So right from the very start, it's easy to see that antiderivatives are much harder than derivatives. What makes them harder primarily is that there's no clear method that you should use to take an antiderivative. You have a collection of strategies, a collection of methods, and your first task is to figure out which one's going to work. And that might mean trial and error. That might mean making a mistake, making an attempt that doesn't lead to a solution, making an attempt that leads to something like this, that's worse, and then you have to go back. You can waste tons of time by doing this, and the more methods of integration you learn, the more time you can waste pursuing the wrong method. It can get very discouraging and it can get very confusing. The only way to get past that is practice, is to do enough problems that you kind of get a sense. As soon as you see the problem, you think, oh, this looks a little bit like integration by parts problem. I'll try that first. And if it doesn't work, all right, I'll try substitution now. Just having that type of a mindset that says it's okay to get it wrong. Because I have 6 methods, so I'll try this. Oh, that didn't work. I'll try that next. It's a good way to start thinking about problems. Here's another type: x times ln of x. So I'm going to say that this is equal to integral of u dv. That is an IBP question, integration by parts question. We'll put a question mark because we don't really know that yet. We don't know that until we try. So the integration by parts formula says that this is going to be equal to uv minus the integral of v du. And we need all the components for that. We need to identify one piece as the u, the other piece as the dv, and then we have to take the derivative of u, rearrange it to get du, and take the antiderivative of dv to get v. What are the options that we have? We have u is equal to either x or u is equal to ln of x. If u is equal to x, then dv is going to be ln of x dx. If u is equal to ln of x, then dv is equal to x dx. So those are the two options that we have right now. Two options for splitting this. Which one should we use? Well, let's think about integrating dv. I won't say easier, which is better. / easier. If we want to integrate ln of x, remember that's not taking the derivative of ln of x. The answer is not 1 over x. We're asking, what do you take the derivative of to get ln of x? We don't know how to do that. That's one of the unknown integrals for us right now. But we can integrate x. The antiderivative of x is just 1/2 x squared. So I would say on that basis, we should use the second option. Choose second option. Easier to integrate. So here we go. I have u is equal to ln of x. dv is equal to x dx. I'm going to take the derivative of u. Du by dx is 1 over x. So du is 1 over x times dx. That can go in the first part, or the last part for du. Now I need something for v. So we're going to integrate dv. Integrate both sides of that expression. We always get v on the left-hand side. On the right-hand side, antiderivative of x is 1/2 x squared. So we'll plug that in. And I should indicate that all this stuff is just thinking out loud. You don't need to write that in a solution. Okay, so let's sub in those pieces. So u, we said, was ln of x. I'm going to need more space. I'm going to write all the way to the edge there. I make the souls of my old math teachers sad by not having equal signs line up. Okay, and then v, we just found, was 1/2 x squared. Minus integral of v times du, v 1/2 x squared, and then du is 1 over x dx. Now we have to clean this up. So putting constants out front, x to a power after that, and then trigs and logs and exponentials in some order afterwards. It's always a good idea to do that. Makes it look more standard, makes it look a little bit more friendly. We can take the 1/2, put that outside the integral as well. And I'm going to do the next part in 2 steps because I don't want to cause extra confusion. This is already confusing. We have an x squared on top. You have an x on the bottom. And we can simplify that. That's just going to be an x. Using exponent laws, the power cancels. 1/2 integral of x dx. Okay, and then we can take the antiderivative of x fairly easily. The antiderivative of x is 1/2 x squared. And we get a big plus c. And then that can be simplified. That's 1/2 x squared times the ln of x minus 1 over 4 x squared plus c. That's our answer. Very mechanical. Once we figure out what to let equal to u and what to let equal to dv, we're just following a formula. We're following a mechanical process. We don't have to think anymore. The thinking step is concentrated in the selection of the u and the dv. Just put some arrows up here just to say that those are not the answers, those are the intermediate steps we're going to plug in. Okay, let's do another one. X e to the 2x. If I let u equal e to the 2x and dv equal x. When I integrate dv, my x is going to become a 1/2 x squared. So my x part is going to become stronger. If I let u equal x and dv equal e to the 2x dx, when I take the integral of that, I'm still going to get an exponential function, e to the 2x, and it's only going to be multiplied by a constant. So it's not going to become more complicated. It's not going to become a higher power or anything worse. So this is a more natural choice, I think. This is according to integration by parts. We can rewrite this as uv minus the integral of v du. I'm going to take the derivative. Du by dx is just 1, so du is equal to dx. I'm going to take the antiderivative of dv to get v. We get v is equal to 1/2 e to the 2x. And I use a substitution there using w equals 2x substitution. And we're going to plug those results in. So u we said was x. And then we just found v is 1/2 e to the 2x. Put that in both spots, 1/2 e to the 2x, and then du is just dx. And we can simplify 1/2 x e to the 2x minus 1/2 e to the integral of e to the 2x. And we can use w equals 2x to do that second integral. But pause for a second. Look at the new integral that's been created on the right-hand side, where we have the integral of e to the 2x compared to the integral of x e to the 2x. So we made it simpler. We made a better integral. So 1/2 x e to the 2x minus 1/2 antiderivative of e to the 2x, 1/2 e to the 2x plus c. And we can rewrite that. 1/2 times 1/2 is 1/4. That's our final answer. So in this problem, we had to use integration by parts and we had to use substitution. IBP plus substitution. And I didn't show the substitution step because it's very fast and I don't want to cause clutter. All right, so the big mystery. How do you go about selecting which thing to equal to u, which thing to equal to dv? And the real answer is that there are exceptions to any rule that anyone can write down. So there's all types of complicated strategies to help you identify which thing to equal to u. The least complicated of the strategies is this one. And even though it's the least complicated, it's pretty accurate. It captures almost all of the problem types that use integration by parts. The LIATE acronym, which is sometimes lengthened to ILATE if we're using inverse trig functions, which we don't have in the course, so I'm not going to include that in the acronym. The LIATE acronym tells you the order in which you look for terms to let equal to u. So the earlier in the word the letter starts, the higher the priority for letting that term equal u. L stands for log functions. A stands for algebraic. That's like x to the n. T stands for trig, and E stands for exponential. So order of letters in LIATE tells you which function type most frequently should be set to U. So it is a frequency. It is not necessarily 100% accurate. Sometimes this acronym will lead you astray. I'll write down a few expressions just to give you an idea how it works. So integral of ln of x times sine of x dx. LIATE says u is equal to ln of x. L before t. Log exponential. Sorry, log and trig. What am I doing? Log and trig. So we have a log, we have a trig. L comes before t, so I'm going to let u equal ln of x. It's really dumb. Like this acronym, there's no hidden universal truth inside an acronym like this, but it's just a way to memorize the order. It's fast. It gets it done, even though it's not 100% accurate. Here's another one. Let's go e to the x times 1 plus x squared dx. We have an exponential and we have an algebraic. LIATE says u is equal to 1 plus x squared, because a before e. The algebraic part in the letter LIATE comes before the exponential part. The a comes before the e. So just two examples, etc. So let's deploy the LIATE acronym to figure out what this antiderivative is, x times ln of x squared. What's a little bit misleading of what we're doing right now is that all these integrals are covered under the umbrella of integration by parts, because this note in this video is called integration by parts. But when you're doing an integral, you don't necessarily know that. So really quick, we're going to use IBP, and then LIATE says we have a log before a, before the algebraic. So we're going to let u equal the log. U is equal to the ln of x all squared. And then dv is everything else. dv is x dx. So we're going to rewrite this using integration by parts as uv minus the integral of v du. Take the derivative, du by dx. We have to use the chain rule. We have a function raised to a power, so the derivative will be 2 times ln of x to the power of 1 times 1 over x. And I'll rewrite that as 2 ln of x over x. So that'll be our expression for, oh, I've got to rearrange, get du all by itself. So du is equal to that times dx, cross multiplying. So that's our du. And now dv, and integrate both sides. Oh, and we get v is equal to 1/2 x squared. We'll plug that in, and we'll plug that in. So u, we said, was ln of x squared. V, we found was 1/2 x squared. Now we have minus integral of v to u, 1/2 x squared. And then du is a terrible mess of stuff. Two ln of x over x dx. And we have to clean that up. 1/2 x squared times ln of x all squared minus 1/2. We have an x squared on top and an x on the bottom. That'll just be an x. And actually, we also have a 2 on top. Gotta be a little careful here. We'll color code it. We have a 2 on top. We have a 2 on the bottom. And we have a single power of x left on top. And our ln of x is still there. So the question becomes, is this any better? We went from x times ln of x all squared to x times ln of x. And I would argue it is better, but we're not done yet. But we're not ready to integrate. So what are we going to do? Well, I'm going to do that integral again on its own off to the side using integration by parts. Integral of